So yesterday we ended off class working on a couple of position versus time graphs, just interpretation and some simple calculations. So that's what I want to start today with before we get back into velocity versus time graphs. Right, today is going to be a day where we're going to be working on those things. If you're not getting something, please ask. Okay, and I will come around and give you a hand and some additional explanation or whatever. Okay, but we're working on graphing today, so get your books open and give that one a try. It's number 3, okay, in your digital workbook, but I'll leave it blown up on the board here. Okay, okay, so you don't necessarily have to do this, but it's not a bad idea, especially if talking things through in your head helps you figure things out. Okay, you probably noticed that I do that all the time when I'm going through a problem. Okay, you got to kind of talk yourself through these graphing questions. And the first thing is identifying what kind of graph it is, because things are different on different kinds of graphs. Doing one operation on a position time graph gets you one thing, but on a velocity versus time graph, that same operation gets you something entirely different. For example, slope. Okay, slope on a position versus time graph represents velocity, but slope on a velocity versus time graph represents acceleration. The calculation is the same, but what they represent is totally different. Okay, so I have to remember what kind of graph am I looking at so that I can start figuring out what each thing I can calculate actually represents. Okay, so the first thing is this is a position versus time graph. Okay, it's showing me where the object is at various points in time. The first thing that the question wants to know is what's the displacement from 0 seconds to 4 seconds? Okay, so I normally calculate displacement. Okay, I normally calculate displacement by going final position minus initial position. That would work because this graph shows me position versus time. Okay, so then I'm going to figure out what's my final position. Well, the end of this is supposed to be 4 seconds, so here's 4 seconds. Okay, and the position at 4 seconds is -4 meters. Okay, minus the initial position. Initial means at time 0. Well, the position is also 0. Okay, so that means -4 minus 0 is -4 meters. Okay, the object went backwards 4 meters in that time. Okay, everybody all right with that? Part B wants to know the total distance traveled. Okay, for total distance, it's about how far in total. That means I keep adding whatever I do onto what I've done already, regardless of the direction. So, in this first part of the graph, I go from 0 to 4, -4, but because this is distance, it's right 4. Okay, how far do I go here? Zero. Okay, my position doesn't change there. That's why the line is horizontal. All right, and then I go from here, which is -4, to here, which is +6. Well, that's 10. Okay, so I've gone 10 meters in one part, 4 meters in another. Okay, so my total distance is going to be 10 plus 4, which is 14 meters. No direction on that because it's scalar. Okay. All right. Average speed over the whole trip. Did I just do half the work for that? I did, because average speed is total distance divided by total time. I just calculated the total distance to be 14 meters. Okay, the total time is 6 seconds. Right, so 14 over 6 should give me 2.3 meters per second. Again, no direction on that because speed, sorry, is scalar. All right, and then average velocity over the whole trip. Okay, so average velocity is total displacement divided by total time. All right, have I calculated the total displacement yet? I calculated the displacement between 0 and 4, but I haven't done the total displacement yet. So, total displacement is going to mean final position minus initial position divided by time. So, my final position is +6. Okay, so +6. My initial position is 0, and my total time is 6 seconds. Well, that's a pretty easy calculation. +6 divided by 6 should be +1 meters per second. Okay, is that ringing a bell for everybody? So now we're going to switch gears and we're going to go back to velocity versus time graphs. Okay, now I have this one, but I feel like I want to save that one. Okay, because it's a lot of work, that one. I would like you to look at question number 5. Okay, now quick review. Things I can get from a velocity versus time graph. The velocity at any point in time. The acceleration. Okay, I can calculate acceleration with this formula. It is on your formula sheet, but we haven't used it very much yet. Okay, acceleration equals final velocity. All right, these are all vector quantities, so we should all have arrows over top. Okay, final velocity minus initial velocity divided by time. And I can calculate the total displacement by going average velocity times time. Now, what does that mean on this graph I'm actually going to do? If I want to calculate the displacement, we kind of did a little trick. If I'm looking at this first part of the graph here, what's my average velocity during that time? Negative 8 meters per second. Because during that first 5 seconds, the object travels at 8 meters per second, and it doesn't change. So that's its average velocity. Okay? And it does that for 5 seconds. So if I just go average velocity times time, I'm just going 8 times 5, okay, actually negative 8 times 5, so that's going to be negative 40 meters. Did I just calculate the area of that rectangle? Base 5, height 8, okay, was that the trick that we used? Okay. Can I do that with a triangle? And a triangle? And a rectangle? Okay, I'll give you a couple minutes. Okay, can I do part A, or get an answer for part A without doing any math? According to that graph, what does the object do? Look at the shape of the graph below the x-axis and then above the x-axis. Are they the same? Like they're mirror images of each other, right? Does that mean it did exactly the same thing backwards as it did forwards? Does that mean it ended up back where it started? It does. Okay, I wouldn't have expected anyone to get that because you don't have a lot of experience with graphs yet. But as you gain experience with graphs, taking one look at that graph says it went forward and backward and came right back where it started. Okay? It traveled at a constant velocity of negative 8 meters per second for 5 seconds, and then it slowed down, reached a velocity of 0, then accelerated over the exact same time period to positive 8 meters per second, and traveled at positive 8 meters per second for 5 seconds. It did exactly the same thing forwards as it did backwards, which means it's going to end up back where it started. Okay, everybody follow me there? All right. So I wouldn't have had to necessarily do any math if I had the experience to read the graph and interpret the graph. Okay, can I prove it mathematically? Absolutely. Okay, so we just did this part here, where the object traveled at negative 8 meters per second for 5 seconds, and we said that that was negative 40 meters, negative 8 times 5. Okay, now, during this part, the object's velocity changes. It goes from negative 8 to 0, which means its average velocity is, that's its final velocity. Its average is, if it goes from negative 8 to 0, its average is negative 4. Base times height over 2. Okay, that height over 2 part is what calculates the average velocity for you. So all we're doing is this formula for this part of the graph. Okay, we're taking the time, which is the base, 5 seconds, and we're multiplying it by the average velocity, which is -8 over 2. Base times height over 2. Okay, and I'm getting average velocity times time out of that. So when I do that, okay, I'm going to get -8 times 5, which is -40, divided by 2, -20. Okay. Then if I'm looking at this section of the graph here, okay, it goes from 0 to +8. Okay, so the height of that triangle is +8 times 5 is 40, divided by 2 is 20. And then this part here is +8 times 5, which is 40. So I've got -40, -60, -40, 0. Okay. Everybody all right with that? Okay. How many people are done B? Okay, I'm going to give you a couple more minutes on B. That's what you need for B. Okay? Can we read the velocity right off the graph? Okay, that's what we have to do. We can get the time directly off the graph. We just got to plug in the right numbers to do B. And you've done most of the work for C already. Okay, you're looking for the average speed over the whole trip. Average speed is total distance divided by total time, and you've done the bulk of the work with that already. Okay, so I'll give you a few minutes to work on B and C, and then we'll go over those. Okay, so in this formula we have velocity final, so whatever the end velocity is, minus velocity initial, so whatever the starting velocity is, divided by time. And for this one here, you are looking at 5 and 15 seconds as your initial and final points. Okay? Give you 5 more minutes. So, if we're looking at B, trying to calculate the average acceleration between 5 and 15 seconds, okay, what we are looking at here is this is our starting point, and this is our ending point. Everybody okay with that? Between 5 and 15 seconds. Right? So if I'm plugging into that formula, Vf minus Vi over T, okay, then T is 10 seconds. Yes? I'm going to go from 5 to 15, sorry, so that's 10 seconds. Now, what's my final velocity according to the graph at 15 seconds? What's my velocity at 15 seconds?
+8.
Right, +8. What was my velocity at 5 seconds? -8. Okay, so I've got +8 minus -8. That's actually adding 8. So I've got 16 on the top, positive 16 divided by 10. So 16 meters per second divided by 10 seconds should give me 1.6 meters per second, or what was the other way we wrote that? Meters per second squared. Okay? Everybody all right with that? All right. Now, average speed. There's no trick to average speed. Average speed is still the same thing as it's always been. Sorry, that's velocity. Speed. Okay. Average speed is still the total distance divided by the total time. Have I already calculated how far the object went during all the parts of its trip? Yeah. It went 60 and then 60. How far did it go? 120. Okay, because it went 40, then it went another 20, that's 60, 80, 120. Okay, I just add them all together because distance is scalar and so is speed. Okay, and then the total time is 20 seconds. Okay, so that should give us 6 meters per second. Okay. Are we doing anything like mathematically different than we've been doing at any point since we started looking at V equals D over T? It's just how we get the data we put in to V equals D over T that's changed. First we got it from word problems, now we're getting it from graphs, but we're not treating it any differently. Data is data. It gets plugged into the formula no matter which kind of question you're dealing with. Okay? All right. I would like you guys to try this one, okay? Because the grid is easier to read on this one. Okay, so it's asking for part A, acceleration between A and B, okay? And then the displacement between A and E. So you might have a few shapes to draw for that one, okay, between A and E. And the acceleration between F and G, which should be very quick, right? And the average velocity between A and F. And then the total distance traveled after that. So, have you got a few shapes to draw? Okay, not for part A, but okay, once you get to part B, I would start drawing all the shapes. So, I'll give you a few minutes. We'll go over part A, and then I'll give you a few more minutes to get all the shapes you need to calculate the areas of, draw it. And then I'll draw them up to make sure that you guys have the same ones. All right, so we got a velocity versus time graph, which means I can read velocity and time directly off the graph, which is what I need if I want to calculate acceleration, which is what part A is asking me to calculate. Right? So the values I need to get from my graph are final velocity, initial velocity, and time. Right? So it says between A and B. So between A and B is a time of 2 seconds. Okay, I'm reading that right off the graph here. So I know t is 2 seconds, right? So then this has to be my final velocity because it is the velocity of the object at 2 seconds. Everybody okay with that? Okay, so I'm just reading my values off the graph. So that's 20, and then my initial value at time 0 is 0. All right, so I've got 20 divided by 2, 20 meters per second divided by 2 seconds is going to give me 10, positive 10, meters per second squared. Okay, didn't have to do any algebra, I just had to find the numbers off the graph. All right, how many people think they got the shapes all drawn for part B? Okay, I'm going to give you a couple more minutes and then I'm going to draw the shapes. Okay, so should you have this drawn out on your paper roughly? Would that be a good idea, a good starting point? Okay. Or draw the shapes out at least with their dimensions or something like that? get the shapes drawn up here. Oh, I left that recording. Okay, so the shapes that we've got to have drawn. I'm going to have this triangle right here. During that part of the graph, the object is increasing its velocity or accelerating. We already calculated the acceleration for that, so we already know that. Okay? Then, if I want to get the displacement for this whole graph, I need the entire area beneath the line, or between the line and the x-axis. Agreed? Okay. So if I want to draw this in as few shapes as possible, I'm going to draw one big rectangle right across here. Okay? Rather than having a whole bunch of small rectangles, okay, why not just draw one really big one? Okay? Then I'm going to have that triangle there. Okay? I'm going to have a rectangle here. Okay? A triangle there, and a triangle there. Okay? Does that take up all of the area between the line and the x-axis? Okay. Now, for part B, it only wants to know the displacement between A and E, so I can actually stop right there for question B. Is everyone all right with that? And eventually, I'm going to need the whole thing because it wants to know the total distance traveled for part E. Okay? At that point, I'll need all of the shapes. All right, I'll give you a few minutes to get the area of those shapes calculated. Okay, so we're going up to this point right here. Okay, we'll try and get through this super quick here. All right, so in this first triangle, I've got a height of 20 and a base of 2. 20 times 2 is 40, divided by 2 is 20 meters. All right, then I've got this rectangle here that's only going to go to 8 seconds. It's 2 to 8, so its base is 6, and its height is 20. 6 times 20 is 120. Okay, then I've got this skinny little triangle here. Okay, the base of that skinny little triangle is 1 second. The height of that triangle goes from 20 to 40, so it's 20. So 20 times 1 is 20, divided by 2 is 10. And then I've got this rectangle here that has a base of 3 seconds and a height of 20, so it's 60. So if I add all of those together, okay, I should get 210, yep, 120 plus 90, 210 meters forward or positive. All right, we're going to work some more on that on Monday. Have yourselves a good long weekend. You don't have any homework from me. What a nice guy. Don't say I never do anything for you. Oh, yeah, but that's not due right away. It's not due Monday.
But we should get it done.
Good point. It's a valid point.
We get more.
I'm really not a nice guy. Have a good weekend, guys.